I did my project on an altitude control for the B-1 Lancer. So just a quick background, the B-1 Lancer is a US Air Force heavy bomber. It's pretty unique because it's a very long range and it is supersonic, which is the only supersonic bomber in the US fleet. And then it also has a variable wing, so the wings can sweep forward and back to achieve those supersonic speeds and to kind of change the way that the plane flies. Designed during the Cold War so that we could strike first deep in the Soviet Union territory. Um, and then over time, it was changed into a design for just a normal bomber. Um, and so when it was initially being designed as the strike first bomber, um, Soviet Union had very advanced radar and surface-to-air missile capabilities. So we had to find a way that we could actually deliver a bomb deep into their territory without getting shot down. So their idea was to have a plane that flies extremely fast at low altitude, so that when the radar tries to detect you, you essentially get kind of mixed in with all the noise and they don't see you with the radar because this was prior to look down radar technology. So they decided to make a supersonic bomber essentially that could do exactly that, fly very low to the deck. And it used terrain following radar so that the plane can look ahead and see what the upcoming obstacles are so that it can avoid it instead of crashing into the terrain. And then this controller will just the pilots don't even have to once they lock in the elevation, they don't actually do anything because it's way too fast for them to be able to. So the plane will automatically maintain that constant elevation, and these are at high subsonic speeds. So there's been pilots that have said they've gone Mach 0.85 at just 200 feet of elevation, which is 650 miles an hour, or 290 meters per second. Which at that speed and that elevation, you essentially have like 1 second of time if you're off on your inputs before you crash. So first thing, control surfaces and axes. So the control surface you can see for the B-1 labeled here. Um, and using the roll pitch yaw standard convention for planes, we have three really relevant control surfaces to control on the B-1. So the first one will be the stabilator, which is a type of elevator where this entire flat part will actually move up and down, whereas the normal elevator will just have a little piece of it that swings up and down. Um, and then we have spoilers on the wings to give it the roll to rotate. And then we have the rudder to change the yaw. You'll also notice that there's flaps on it. That's more for a lift thing and landing, as well as canards, which are sometimes used on other planes as control surfaces in the roll pitch yaw axes, but these are used to maintain limited turbulence when you're flying at such high speeds with such a large plane. Um, and then the variable wings, that's more of a lift to velocity ratio. So they push them back when they're going really fast and pull them out when they're trying to take off and land. So that's also not really a relevant control surface in terms of what I'm trying to do. And then we're using the roll pitch yaw for the body, but then it's also common for planes to use this northeast down convention, which is your positive x direction will be traveling north, your positive y will be in the east direction, and then positive z is downwards. So when you increase in altitude, you actually have a more negative z, which is just something to keep in mind for when you're designing your controller to just be careful of the sign convention. So I started with the aviation systems library, and I had a ton of issues. Um, but so the aviation systems library, it has this is their best example model for interacting and doing control stuff that I wanted to do. So in the aircraft, you have your propulsion type, and then it takes in the elevators and the throttle as inputs, and you also have landing gear just for the visualization stuff. So the main problem with that is that your dynamics essentially depend on your propulsion type and your elevator angle and your throttle to stabilize. So you have this kind of weird balance where you have to maintain a speed, you have to have the proper elevator angles and throttle. Um, so you really have like a multivariable system, um, and this just leads to a ton of problems with stabilizing it. So I tried to use a just a PID controller, and I used the exact steady state conditions that they had in their example, and I wasn't able to replicate stability, which is pretty much what led me to use my own dynamics. And so the major limitations also are that they use a 2D model, so they don't actually have um, roll or yaw capabilities, so you're stuck in only 3 degrees of freedom, and then you become speed limited because of the propulsion types that are available, as well as, um, because it's a multivariable system. And then I don't have an aero background, so the, complex aero makes it really hard to debug, and their documentation is just not great overall. So for mine, I used, these dynamics, which I found from some papers online, that essentially simplify the system. So you have just a couple inputs and variables that relate to roll, pitch, and yaw, but aren't exactly the same as the previous system. And so you have your XYZ positions, and then your yaw is done by a heading angle. Your pitch is by that flight path angle, which is similar to angle of attack, so how much the plane is tilted up, but a slightly different convention. And then you have your bank angle for roll. Um, this model also allows you to have a constant velocity input. So where I was speed limited and I couldn't model the very fast plane in the first part or in the library version, this lets me do essentially any speed I want, which is important for the B-1. Um, and you also have 3 inputs. So you have a easy way to accelerate. The most important for this project will be that pitch input, where you have the flight path angle, and this will just let you climb and descend as needed for the altitude controller, and then bank angle, which controls roll, and then in conjunction, when you roll, you can induce yaw. Um, so some of the assumptions with this are that this is essentially a point mass plane, and this is done so that we can neglect the aero stuff that we don't understand. Um, but this is pretty reasonable because we're using a system, we're trying to model a system which is still classified and in use by the military. So a lot of the specific details about the plane, like your mass distributions and your lift, that's all classified. So we can't actually model that exactly. So we need to do it this way. Um, and then the interface with the control surfaces, our control surfaces essentially become psi, phi, and gamma, where our pitch, the most important one, will be controlled by gamma, our flight angle, and that essentially is our stabilator interface. So we won't have a direct stabilator in the system because we're just using systems of equations, but we'll have essentially a mapping to it. Same with roll, that gives us our spoiler interface. And then we don't technically have a rudder interface because yaw is a function of the bank angle. Um, and so the yaw will be, you'll have to rotate the plane to turn. Um, this is actually a pretty reasonable assumption because with the rudder, it is hard to turn um, without actually inducing a roll. So if you see normal like fighter jets turn, you'll notice a lot of times they kind of go inverted to do heavy G turns that aren't like pulling straight up. This is kind of the same principle where their lift ratios are affected by um, the design of the wings. And so a lot of times the highest G turn that you can do will be taking advantage of your flight angle and adjusting that accordingly to get those high roll and yaw turns. Um, this also this model also lets us do the speed changes pretty easily without having to worry about propulsion, like I mentioned before. And then the most important thing is that our altitude controller can output gamma, and it will only take in a single input, so it makes the system uh, much easier to design than multivariable. And then we're going to use a massless spherical payload, so just a ball essentially floating right on the bottom of the plane, and it's carried externally. This is fine because in the real system, the B-1 has an entirely internal payload. So there's none mounted because it's at such high speeds on the external wings. So we wouldn't see any interference between the mass and the actual dynamics of the plane. And also the B-1, as with most planes like this, they're more limited by the airframe because it's so fast, where the mass of the bomb prior to and post deployment is really going to be pretty negligible in terms of the actual speeds and dynamics it can attain. So this is my full model. You'll see this is my plane model with all the equations defined in here, and then it just spits out all those variables and takes in all the variables from that table from earlier. And then we can see we're outputting our z, which is going to be our negative altitude because of that negative definition. So we just invert that, and then we can use altitude normally for everything else. Um, so first off, get this out of the way. That's just the visualization stuff for later, where we have a 3D model and then the rest of the things in the visualization. We have a series of altitude commands to kind of model a reasonable path that a plane might take. Um, and then phi and v, those are going to be kept constant for our designs because we're just going to work in 2D, so we can mainly focus on the altitude dynamics. And changing speeds fairly trivial since it's just a constant essentially. So it's not that important to change for us. And then here we have the terrain modeling. So this uses a Gaussian noise where we have a standard deviation of 20 meters. So we get essentially hills up to 30 meters or so that the plane has to kind of recognize and avoid with the controller, which is a reasonable task to be able to do. And then we filter this so we don't get discrete measurements and it's just a little smoother. And then we also only start using the terrain as reference below 250 meters so that we're not bouncing all around when we're essentially at cruising altitudes. And so this is just the logic to implement that. And then this goes into our controller where we implemented a PD controller. Um, this will have some more talk later, but yeah, so we have our altitudes and then we use the input desired altitude plus the noisy essentially readings. So we have like, say we want to maintain 200 meters of elevation. We're at 200 meters plus or minus the ground noise where the ground is varying over time. And so I made a terrain following controller. So this is essentially a more advanced altitude controller because if you can maintain altitude, um, the next step is to maintain altitude for a much more varying system. So I used the linearization in Dymola, and then I exported that to MATLAB and used ISO tool to eventually land on the PD controller. So this was our transfer function of the system for the constant um, phi and velocity, where gamma is going to be our input and z is going to be our output. Um, and so you can just see that it's basically just constant velocity over our two poles. And then this is just the basic controller definition. So in ISO tool, I got KP of that and the time 2.5. And then I didn't really like the performance with what I was seeing compared to the terrain. It was a little too slow. And it also had overshoots, which you can't have overshoots if you're trying to avoid the ground. Um, so that was what led to these tuning parameters. And in this plot, you can see the actual altitude of the plane with the controller active. So this green is going to just be our ground. You can see it's got that varying around zero. So this is essentially like a hilly environment with that up to 30-meter essentially hills. Um, and then if we overlay that, the red gives us the altitude that we want to maintain. And then the blue is the actual altitude. So you can see the altitude is tracking very well. And we're never getting too close to the ground where we're in risk of crashing. Um, there are minor spots where it clips through, so maybe you're trying to maintain 100 meters here, but with the small oscillations and the varying in the hills, maybe you only go down to 90. We're probably still safe as long as you don't try and maintain an elevation of 10 meters, um, which is simply not needed. And then for the actual path of the plane, I tried to model a kind of similar path which a plane would have. So start at 0 altitude, take off, and quickly rise to some elevation. And then you continue rising, so you're at, like, kind of a, cruising altitude, so up pretty high, and then you stay at that for a while, and then in real life, when they do these missions, they will go down, level off, and then go down again to their final lower level. So you go down from 1,000 meters to 250, and then once you're stable at 250, you drop down to your 100 to essentially initiate your bombing run, um, and then stay at that for a while because we're avoiding the radar in the terrain, and then we land at 600. So here is the most complex animation I have. You'll see plane takes off, the payload is here, that green little circle, and then we're tracking the plane. So we've just gone up to essentially cruising altitude, so we'll be at that for a little while, and just maintain this. And so we just continue at cruising altitude, and now we've done our first level off to that lower value, but we're not at our final approach yet. And now if we wait a little bit longer, we'll start approaching. So we're in the final approach now, and then you'll see a white cube appear quickly, and then the payload will drop into it, essentially completing the bombing run. You'll also notice these small up and down movements of the plane. That's essentially the tracking of the terrain, which wasn't modeled in the visualization, but is still there essentially. Um, and now it should be dropping soon. And so drop the payload, plane continues on, and then it goes and lands. So it was very quick. So I put a couple just frames of dropping the payload. So we can see this is going to be our target. This is our plane, and the payload has just basic kinematics equation, and it just drops payload with free fall and forward velocity. And then you can see here it's intersecting the target building, which is a successful strike essentially. And then so just a quick conclusion. Um, I have a 6 degree of freedom strike capable model, so my plane that I modeled can actually deploy payloads on a desired location, um, and can move in all 6 degrees of freedom. So we can turn, rotate, forward, backwards, up, down, um, which was kind of important and a key thing which the flight library wasn't able to do. And we used that terrain following. So the main goal was to get that controller working, and it worked pretty well. We had the visualization of the B-1, and we also had the simple payload ballistic modeling using just standard kinematics, as I mentioned. And then if anyone else wanted to keep working on this for whatever reason, the one key thing would be to work on aerodynamics. So if someone had a aero background, this would be a good project for them. And then I did a 2D path because I was only focusing on the altitude controller. But if you did a 3D path, you could incorporate some cool path planning stuff and obstacle avoidance with like surfaces, which would be kind of interesting, I think. And then I essentially used look down terrain sensing, where I just took the measurement directly below and I translated that up. Um, the actual plane uses forward looking, so it sees ahead of it to do it so it can get lower to the ground. So kind of changing the sensing method, that could be a something to update. And then in the animation, as you saw, the plane kind of just translates forward. Um, but you could, if you had enough time, actually incorporate the rotations from roll, pitch, and yaw into the animation so that that 3D model actually kind of turns in space, um, which would make the animation pretty cool. And then finally, the B-1 has an extremely large payload capability. It has 75,000 pounds of payload. So it a lot of times it doesn't just bomb a single location. It carries multiple payloads for multiple targets. Um, so if you wanted to do something with multiple payloads where you have a 3D path and you kind of hit them on the way as you zigzag through the environment, that would be pretty cool as well. And then that's it for my modeling and simulation project for the semester.